This movie is about a Herculean volunteer endeavor by the Fort Stanton Cave Study Project. Mold began to grow on the wood bracing almost as soon as the dig between Don Sawyer Memorial Hall and Mud Turtle Passage was completed. The wood softened, creating a safety concern. So a plan for a more permanent solution was formulated using stainless steel and high-density polyethylene. Filmed between August 23, 2009 and April 28, 2011 and was released on DVD in 2012. This video documents fabrication and installation of the stainless steel replacement structure. November 2003. Initial explorations end. A revelation. The white frosted river of stone connects through the Turtle's terminus to the base of Don Sawyer's massive breakdown. Excavated passage deemed unsafe. A new gate built, and locations verified by invisible waves of radio emissions. To access the river of snow, a new dig is born. Sheathed in wood, a structure is created to brace the excavation against the inward force of earth and rock. But a silent menace begins to devour, and as the wood softens and loses strength, a more enduring solution was formulated. A stainless steel and high-density polyethylene replacement designed by Steve Pierman, a director of the Fort Stanton Cave Study Project. The fungal infection had progressed quicker than anticipated. Therefore, it became a race against time. And so, the Fort Stanton Cave Study Project embarked upon the task of replacing the Don Sawyer Memorial Hall to Mud Turtle Passage support structure. Water in the measure of 27 gallons transported to Don Sawyer Memorial Hall. Support structure footing area enlarged to 5 foot by 6 foot. The floor lowered 6 inches to expose maximum bedrock. And finally, measurements were generated at the bottom for the foundation, along with the measurements of each frame corner on all levels, using a plumb bob, all accomplished throughout the July 2009 expedition. The wooden structure, constructed from the top down as the dig progressed deeper. But the replacement would need to rise upward from a concrete foundation at the bottom. August 21st, 2009, with water in place and measurements secured, a team consisting of Jim Cox, Ed Payton, Rick Reynolds, and Lloyd Schwartz began to repackage concrete into 10-pound parcels, placing an 80-pound bag in a plastic mixing tub. A hole is cut in the side of the bag. A small scoop was used to fill a container that was fabricated to hold 10 pounds. First, a normal Ziploc bag was filled with concrete and sealed. Then it was placed into a heavier 4mm Ziploc bag. And lastly, duct tape was used to keep the bags packed tight and for added strength. At the conclusion of the evening, 15 80-pound bags of 5,000 psi quick-setting concrete was transformed into 110 10-pound sacks. In order to fill the foundation, an additional 12 80-pound bags of concrete would need to be processed. So, on August 28, 2009, Jim Cox, Cal Currier, Grace Currier, and Rick Reynolds performed the same procedure. The normal Ziploc bags have a better zipper than the 4mm and were easier to seal. Any concrete dust in the zipper of the 4mm bags made them almost impossible to seal. Double bagging made them strong enough to withstand the rigors of being transported in backpacks a mile through the cave to the foundation site. By the end of the night, the second team had finished packing 90 bags. In all, 200 bags made their way to Fort Stanton Cave and were waiting for the cavers of the Fort Stanton Cave Study Project to convey them to the foundation site on the first day of the October expedition, September 26, 2009. 10-pound bags allowed the individual cavers to pick the amount of weight they felt they were capable of carrying through the rugged cave passages. A total of 35 cavers entered the cave that day, most making multiple trips, carrying rebar wrapped in foam to protect the epoxy coating, foundation bolt locator frames, and bags of concrete. The construction materials were stacked in a pile upon reaching Don Sawyer Memorial Hall, as there was additional work to be completed at the foundation site before pouring concrete. The next day, the excavation at the bottom of the dig shaft was completed in preparation for pouring the foundation, and the concrete and water from Don Sawyer Memorial Hall was transferred to the bottom of the dig shaft. September 28th, a team began their day by fabricating a screen to separate the gravel from the clay and sand, and began sending buckets of gravel to the foundation site to produce a level floor. With the floor level, Steve Pierman and Roger Harris began to assemble the stainless steel foundation bolt locator bars. They first installed the long all-thread rods in pre-drilled holes. These rods would connect the first course of bracing to the foundation. And then bolts were added to the ends in order to connect the locator bars together. After the locator bars were placed in the foundation excavation, Cal Courier began to remove the epoxy-coated rebar from the foam packaging, and then to facilitate adhesion of the concrete to the rebar, Cal wiped any mud that had accumulated on the rebar from their long journey to the excavation site. Steve made adjustments to the locator bars to square up the all-thread bolts and finished up by leveling the locator bar assembly in the foundation excavation. Wayne Walker placed epoxy-coated rebar on the squared and leveled locator bar and then used wire to prevent the rebar from moving around. Crossbars were positioned and every joint wired together to complete the rebar foundation locator bar assembly for the next day's concrete pour. But there were other tasks to accomplish the next morning before the pour could commence. Pat Sawyer cleared the upper levels of the dig shaft of soil and rock to prevent any debris from falling into the fresh concrete. Steve and Wayne spread plastic sheeting in the connection room at the foot of the dig to catch any spills from the mixing operation. Level strings were installed by John Lyles and Robert Dara to mark the height of the foundation upper surface. With preparations completed, the mixing process began.
Coming down. Got it. That's one.
Yeah, let's get some more water in.
At some point, we want to turn at that.
See if you can keep track of, how much water we're using for those, like 3 bags.
All right. We used, what was that, a half gallon?
Yeah,
More?
More, yeah.
That's the third bag.
Okay, let's just do 3.
Okay.
No more than that.
Yeah, just dump a bunch more in.
Wet.
The water at first.
Water time?
Yeah, just a little though. Not too much.
Okay.
Maybe a little more. Yeah, it's got pretty dry. And that's enough on the.
Yeah, that's a good batch.
I think 3 is optimal.
How did that go in the
as far
hole?
as mixing.
Hey, we got one ready almost. A little more mixing. Well, yeah,
water
not
in
mixing.
it. Yeah. Okay.
That was probably now 2 liters. It's about 2 liters.
Yeah, well, we put in 4 bags, so.
Oh!
Yeah. This is a little bit.
Get that corner there. All right, here we go.
All right. Yeah, that's a little wetter.
Here you go. Yeah, it looks a little wetter.
Yeah.
It's a little heavier.
Okay, please, here's more bags. Who else is down there? Where'd they all go? Give me the.
Yeah. A better job, probably.
Right now. We need more powder, buddy.
Good.
With the foundation filled to the brim, Pete Lindsley troweled the surface smooth.
So that's why I said, when I estimated, I went 10% over I thought we would need. Which, has turned out to be probably 20% more, but still.
A couple of days later, Steve led a trip to the foundation site for a few additional measurements and to remove the bottom 2 levels of wood bracing. After a whirlwind marathon fabrication session, the bottom levels of stainless steel were ready for the special expedition, October 31st to November 1st, just before cave closure for the season. The plan was to install the 2 lower levels, to expose any design flaws, improvements in fabrication procedure, and to hone the installation techniques. The bulk of the fabrication was slated for over the winter months, and the trial levels would help facilitate any modifications that needed to be accomplished ahead of time.
Some of the holes may not line up, which is not a big deal, because we have a drill, we can drill them out. However, whenever you drill your stuff, it's got to be done over a piece of plastic.
Okay.
You put locks or regulars? They should use the regulars.
Just flats.
We know what to drill.
Well, plus we're going to have to wait for the drill. The drill's on the hole anyway.
Right.
Well, we got 3 started, which is good.
We can use a government
three.
lock.
Yeah, I got one here,
Don't
one there,
force,
she's got
use
one
a
there.
hammer.
Let's, I think we should put the nuts on these.
Just throw it, yeah. Bag of lock washers for the inside.
Yeah, the locks should be safe for the frame. Who brought the wine? Do we have enough regular washers now?
I got to find out where they went, but I have some.
Got the bottom, Pat. Got the bottom. I've got the bottom.
Got it.
Okay. Bring it down. There we go.
Okay, I'm going to step down.
And I can take and support the weight up here.
Okay, go ahead. And
The first panel.
Got it?
yeah.
Okay.
Okay, which?
Steve, you want another one?
No, one.
Okay.
Moment.
I'll let another one up there until we need it.
They got tapped in heavy.
Do you think that this rock right here needs to come off?
Good.
It's sitting right at vertical right now.
We're going to have some clearance problems right here. We're going to have to bring down some of this stuff. I can see that right now. Okay.
Second panel coming down.
I have it.
Okay.
Which side is this?
Upright corners next?
Send the door brace down.
What?
Well, we need
We need
the uprights.
we need another upright.
Upright and bolts.
Okay, can you lift up on that end, Pat? Just a hair. Okay. Right there, right there.
That drill, because we're going to have to take part of this off.
It might connect to Snowy River.
What we can do, also, if we think we're shy on washers, just put that in there to hold the space. And then we'll tighten these others up, and then later we can come back.
Still,
Yeah, we're gonna.
you got to see them rocks don't face.
Is there another wrench? You got another wrench there in front of you?
It's going to take cement.
Half inch?
Yeah. Tighten these ones all up here.
Those are all half inches.
I'm not sure.
They're in a bucket somewhere. What?
Can you come up? They're handling a panel down.
Oh, we don't want the
We don't need the panel down. Tell them to hold it. Hold it on a ledge.
Let's trap Kenny in here with it.
I don't know. Something, a spacer in between these things?
All right, panels at the next level.
So that we can have a little bit of play in the vertical. You see what I'm talking about?
Up and down?
Because right now, we're planning on no clearance at all. And if you're off a little bit, you're screwed. Are they going all the way to the bottom?
All right, my bucket's coming.
Slowly flames back here in the back.
After successfully installing the first 2 levels of stainless steel and high-density polyethylene, the fabrication began in earnest. The goal over the winter months was to manufacture all levels to 11 for installation during the Spring Expedition 2010. The replacement structure was constructed of a repetition of a few frame types bolted together, along with polyethylene decks and aluminum ladders. The fabrication process begins by placing a 2 by 2 by 1/4 inch stainless steel angle iron on 2 roller stands, with the one end of the angle iron resting on a 14-inch abrasive saw sitting on a heavy-duty workbench. After measuring, the angle iron is secured to the saw at a 45-degree angle and cutting is initiated. When all the sections are cut out of the 20-foot-long angle iron, the other end of each part needs to be cut a second time, as the angle is in the wrong direction to construct a square. Precision is essential at this point, so a measuring jig is employed to guarantee consistency. The trigger is locked to the on position, and a weight was used to provide downward force so other tasks could be accomplished during the cutting process. As the saw worked its way through the metal, the burrs left over from cutting were removed so the pieces would fit in the welding jig. 2 levels were fabricated at a time with anywhere from 60 to 75 cuts. A total of 1,199 cuts were made during the duration of the project. Angles stacked and wheeled to the drill press. Another fabrication session is set in motion. A jig aids in precisely locating the pilot holes. These small holes lessen the amount of force needed to drill out the larger holes and help maintain accuracy. A pump circulates water-soluble oil to keep the drill bit and stainless steel cool. This is important because when stainless steel heats up, it increases in hardness, which dulls the drill bit. Oscillating the pressure on the drill breaks up the shavings into smaller, more manageable chips and aids in cooling the tip of the drill bit. Three 1/8-inch holes were used to bolt the high-density polyurethane to the stainless steel frames and to bolt the levels of frames together. Seven 16-inch holes were drilled in the short sides of the frames, which bolted to the uprights. The extra clearance of the larger hole was to allow for adjustability between levels. The replacement support structure has 3,145 holes, all of which were filled with bolts during the construction. And if you include the fact that every hole was drilled twice because of the pilot holes, the real total was 6,354 drilled holes. The drilling process left a razor-sharp burr, which needed to be ground off the angle iron frame components. By this time, frame components were covered with cooling oil and dust from the grinding and cutting operations. To prevent contamination of the welds, they needed to be scrubbed with heavy-duty industrial heat greaser and rinsed. When dry, the components were placed into a squaring jig. This fixture, fabricated at an earlier date, eliminates the need to measure and square up each frame individually. The frame components were cut a little short so they would fit the jig without having to be pounded with a hammer. The extra play was broken up evenly between both ends to ensure the holes in the angle iron were centered within the squaring jig. The first step in the welding process was to spot weld the corners. Because weld splatter builds up, the frame is removed from the jig and these small welds hold the frame together until it can be welded off. Clamps hold the components tight to the jig, and once spot welded, the components are no longer able to shift position, so the clamps are moved to the next corner. Spot welding each flange of the angle iron keeps the frame flat and square. The replacement structure's most common frame was the Type A, which used an 1.5 inch by 1/4 flat stock center brace to help support the center of the high-density polyethylene panels that bolted to the angle iron framework. When the spot welding was concluded, the frame was removed from the jig and the process repeated until all the frames for the next 2 levels were ready for welding. A MIG welder was used to fuse the inside of the frames. MIG stands for metal inert gas. The metal is a stainless wire fed at a constant rate. To avoid jamming, because of the inflexibility of stainless steel, a spoolmatic MIG gun was used instead of a standard MIG gun in which the wire is fed through a long cable. When the gun is triggered, rollers powered by a drive motor feed wire from a 2-pound reel mounted on the back of the gun, and the wire is energized by the high amperage power supply. At the same time, a gas solenoid allows the inert argon shielding gas to flow from the nozzles surrounding the wire, shielding the arc and molten metal in the weld puddle from oxygen in the atmosphere. Even though spot welds hold the frames together, they still need to be clamped to the table when they are welded off. The heat of the welding process can cause the frames to warp. The high-energy welding arc also emits ultraviolet radiation, which can burn the retina of the unprotected eye. The welding hood has a lens that is opaque to ultraviolet radiation. Its dark tint shades the intense visual light emissions. The hood also shields against infrared heat emissions to the face. Two vertical down welding passes were performed on each joint. The first, or the root pass, was run fast and straight down. This filled the corner and helped maintain the length of the wire stick out, which affects the characteristics of the welding arc as the second pass is weaved down the seam. The back and forth weaving motion was used to increase the width and the buildup of the weld bead. When the bottom of the vertical was reached, the weld continued on along the flat portion of the joint. The height of the buildup and the overlap on each side of the seam should be equal to the thickness of the parent metal of the ideal weld. Because the front sides of the frames were to be ground flat, a TIG welder was used to limit the amount of buildup. TIG stands for tungsten inert gas. A tungsten electrode, which is not consumed by the arc, is utilized in place of a wire feed. Again, The arc is shielded from the atmospheric oxygen by inert argon gas flowing from the nozzle. A foot pedal is utilized to turn the arc on and to control the amperage. In this case, to keep the weld flat, no filler rod was used. A circular motion with the torch helps to force the edges of the seam to fuse together. Because of the direction of the DC electrical flow, the plasma of the arc is concentrated on the stainless steel frame rather than the tungsten electrode. By the conclusion of the project, a total of 5,012 inches of weld was laid. This equates to 418 feet. The welds are ground flat to ensure that the frames fit together without interference, and the high-density polyethylene panels lie flat upon the frame's outer surface. In each corner, uprights were utilized to bolt the frames together to create the box configuration of the replacement structure and to tie each level together. Because of the proximity of the structure to the breakdown of the dig shaft, wrenches could not be used on the back side, so the nuts were welded to the uprights. A simple tool was used to center the nuts on the holes drilled in the angle iron. In all, 860 nuts were welded to the replacement structure components. The heat from the welding process transferred through to the tool, which needed to be cooled between welds. The uprights varied in length depending on the application within the structure. They had bolts welded every 6 inches to align with the 7/16 inch holes drilled in the sides of the frames. The intense heat of welding warped the threads within the nuts and made it hard to thread bolts into the upright. An impact wrench was adapted to turn a tap, and the threads were chased to clean them up. To lubricate and cool, the tap is dipped in water-soluble oil. As the tap cuts the threads, the chips build up. Reversing cleans out the chips. When cool, the weld joint was covered in an iron oxide coating, smoke residue, and surrounded by frozen sparks known as dingleberries. All this needed to be cleaned up, especially the iron oxide coating, to protect the stainless steel from rust. The first step was to wire brush the smoke residue and chip the dingleberries off with a chisel. A more aggressive method was needed to remove the iron oxide coating, so the welds were sandblasted using aluminum oxide abrasive. The welds looked clean, but because the abrasive was recycled, the iron oxide residue left over in the abrasive smeared on the sandblasted surface. A chemical process called pickling removed the deposit. A combination of nitric and hydrofluoric acid in a paste form, the pickling compound removes the leftover oxides and iron contamination from the weld area. The pickling compound also removed the colorful heat tint, which is an oxide layer and chromium depleted zone from the nuts welded on the uprights. After a suitable amount of time, typically an hour, the pickling compound is removed by rinsing and scrubbing the area of application. The next process is passivation of the weld area, a chemical treatment with a mild oxidant to remove free iron from the surface and speed up the process of forming a protective passive layer of chromium oxide, which is what makes stainless steel resistant to corrosion. Removal of iron contamination from the surface of the stainless steel not treated with pickling and pacification is the final step in preparing the frames and uprights. By brushing on a layer of phosphoric acid and allowing an overnight soak, any iron or rust smeared on the surface of the stainless from transport on iron trailers, dragging across the welding tables, or any other contact with mild steel was removed. After rinsing, hanging, and drying, the pieces are ready for transport to the Fort Stanton Cave Study Project bunkhouse, where they would await transport into the cave. 747 hours were spent fabricating the stainless steel frames and uprights. As winter progressed, Steve Pierman and Stephen Fleming cut and drilled the high-density polyethylene panels that were to bolt to the stainless steel frames. Then, using the frames that had already been delivered, they fabricated the decks upon which the ladders were to mount to. With spring's arrival, the construction of the structure began in earnest on April 17, 2010. The Southwest region of the NSS held their spring regional at Fort Stanton Cave and transported 250 bags of concrete and 15 gallons of water to Don Sawyer Memorial Hall. Between April 18th and May 1st, 2010, Hank Boudneau designed and built carrying harnesses with foam padding for the 38-pound stainless steel frames. And he, Evelyn Townsend, Stephen Fleming, and Mike Bilbo used them to bring many of the frames and panels into the cave in anticipation of the upcoming expedition. Saturday, May 1st, the expedition began. Using the harnesses, members of the Fort Stanton Cave Study Project carried the frames and high-density polyethylene panels the rest of the way to Don Sawyer Memorial Hall. It was fairly easy to carry the frames on level trail, not too difficult when using hand lines on some of the moderate hills. And when steeper hills were encountered, the frames were passed chain fashion. At the uphill crawlway entry passage of Don Sawyer Memorial Hall, another chain pass was used to convey the materials to the staging area. By the conclusion of the 9-day expedition, all the frames and panels for levels 3 through 12 were carried in. Assembly began at the Don Sawyer Memorial Hall staging area, with a high-density polyethylene panel bolted to a corresponding frame using stainless steel bolts and washers. Once tightened, it was often necessary to trim the edges of the high-density polyethylene panels to maintain the alignment of the frames in the structure with the uprights. Before construction of additional levels could commence, excavation of the walls was necessary in some places, as the wooden structure was not exactly vertical. The spoils accumulated at the bottom of the shaft, where it was loaded into buckets and hauled up.
Up! Up!
Up.
Once at the top, the spoils were dumped into a sifter where dirt was separated from rock.
That's a nice soil there.
The gravel was used as aggregate in the concrete mix, and the dirt, along with larger rocks, was used to fill between the new structure and the excavated dig shaft walls. Weighing almost 60 pounds, the high-density polyethylene and stainless steel assemblies were lowered down the shaft with a rope. Before installation, it was essential to clean off the mating surfaces of the assemblies, as mud caused alignment problems, and to run a wire brush through the holes in the assemblies and the threads in the welded nuts on the uprights.
Out good, make sure we don't get any dirt in here so that the screw won't gall on the nuts. Okay, I think that's ready to go up in the corner.
Okay. Is your surface clean there?
It's pretty clean. Now, I didn't clean it all the way down by my foot.
Okay. This is pretty clean here.
I think it feels pretty clean.
Okay, so you got the end.
I got the end.
I got the weight. Okay. Okay, set it down. Don't get the mud on your toe.
Now, my toe is in the way.
Yeah, get your toe out of the way.
I got
you ready?
I'm in here. All right. Okay, we're good on this one. We just got to come down. I think we can. Yeah. See what these sides are looking like. Whoa.
We're down.
Yeah, we're down and we're maybe a little too far down. We need to make sure these stop hitting it. Okay, we are close to putting bolts in all of those holes right there.
Let's start with the bottom. With the bottoms.
The use of anti-seize compound prevented the bolts from galling and seizing, which is a problem with stainless steel fasteners.
We'll leave these guys loose till we get the other panel in.
Yep.
Yeah, that's started.
With the bolts tightened, backfilling behind the walls of the support structure was begun to minimize any potential shifting of the breakdown, which might compromise the integrity of the structure.
Behind you is rocks.
Rocks.
Oh, I see it.
Okay, you want me to clear this pad off here?
Rod
Yes.
coming up.
Okay. Yes, please.
Yeah, it's coming. I'll get that off. Well, you want me to fill that bucket?
Thanks.
We don't want to send this.
No, I want rocks in that bucket.
Okay.
And so any rocks that you find in that stuff, keep up here. Okay.
Yeah, you are.
You okay?
No. I'll say what okay.
By day's end, on May 2nd, the support structure had risen from level 2 to level 5. Perhaps the biggest surprise of the expedition occurred on May 1st, when Henry Schneiker and Deirdre Hahn went to Snowy River and found the water to be running. A team had just been there on April 11th, and Snowy River was dry. The downloaded data from the sensors that had been left in Snowy River showed that the water appeared on April 22nd. Back with a vengeance, the eddies off Turtle Rock rolled in an aquatic ballet not seen since August 2008. The island, almost completely submerged. Only the tips of the highest peaks pierced the surface and twisted the water into a string of knotted vortex. The appearance of water led to the cancellation of numerous scheduled science and exploration trips down Snowy River. The construction, however, continued on. With time, certain modifications became apparent. Larger holes were needed for more clearance where the frames bolted to the uprights. Some of the uprights were cut because they were just too long to handle efficiently in the dig shaft and required too many wooden panels to be removed from overhead, which was a safety concern.
It's going to come right off, I think.
In order to prevent a collapse of the dig shaft excavation, some of the larger rocks were split in place using a hammer drill, feathers, and wedges. First, a line of 3/8 holes were drilled in the rock. Feathers were placed in the holes with the ears facing the direction of the desired split. Then the wedges were struck with a hammer, driving them between the feathers. Eventually, the pressure caused a crack to form through the holes and the rock split apart. Wayne Walker installed some wire mesh in the wooden portion of the dig shaft to catch gravel that had been raining down on those working below. In spite of the modifications, the levels stacked up as the May expedition progressed. The average size of the lower 7 levels was 48 by 48 inches, but at level 8, the limestone wall jutted into the dig shaft area, causing the opening to narrow to 32 by 48 inches. The addition of some triangular frames transitioned the lower levels to the narrower mid-levels.
All right, here's the second beam.
No problem.
Eyeballed up.
Up rope. Look like you're still playing with the first one.
Yeah. Oops.
To better accommodate the irregular nature of the excavation as the top of the limestone wall was attained, slots had been cut into some levels to allow some measure of adjustability.
I didn't get any C's on them.
Well, we know we're not going to have alignment problems later. Okay. Back panel.
Ready for the third? Okay. So once all three of them are in, no, you wait for everything's in place before you tighten everything up?
Yeah.
Yeah. So we put these three in. The two corner angle irons that are 8 feet long or 6 feet long, and the two C-frames. Then we tighten it all up and start backfilling.
Saturday evening, May 8th, 2010. The expedition was wrapping up. The stainless steel replacement structure was completed through level 10, and level 11 was essentially ready to install. Fabrication of the stainless steel frames continued after the spring expedition, completing all the levels to 17. But a surprise awaited us for the July expedition. On May 24th, disconnected pools of water were reported in Conrad's branch of the main corridor by a group heading to the dig shaft to finalize some measurements. By June 7th, the pools connected and water was flowing from Inscription Rock all the way to the sewer pipe. Water and slippery mud challenged the teams hauling materials to down Sawyer Memorial Hall during the July expedition, which began on the 3rd and ran until the 11th. As the water was rising in Conrad's branch, the flow had ceased in Snowy River, and the eddies had vanished. The small ceramic tiles left in Snowy River were an experiment to measure the rate of deposition of calcite. By Tuesday the 6th, levels 11, 12, and 13 were installed, and the concrete was being poured around the footings beneath 13.
Oh, okay, got them both.
The next levels of old wood shoring were removed. To properly offset the next level and aid in measurements, a small fill panel was bolted to the uprights. To install level 14, the limestone floor had to be leveled in the rear panel area. The rock work was finished up the next day. Then level 13 was backfilled with concrete rock mix, and finally, level 14 was bolted together. By Friday the 9th, the sides of level 14 had been backfilled, and most of the sides of 15 bolted to the structure the day before. So the day started off with backfilling the end of level 14 where the shelf was to be installed in order to take up the space left by the small fill panel.
Dirt.
More than that?
Yeah. Alright. Never mind. I don't want dirt.
Dirt.
After a few buckets of dirt, it was now time for some concrete.
Get this side.
Okay. The concrete mixed in Don Sawyer Memorial Hall was pretty much the same as that for the foundation, with one notable exception: the addition of medium-sized gravel collected from the screening operations helped stretch the mix to minimize the number of bags needed to be hauled into the cave.
Concrete. Here comes some concrete.
Rope up.
Up.
Concrete on here.
Yeah, up rope.
We did put a lot of that.
Wayne. More concrete?
They're getting more.
You got some more
Yeah.
coming. Yeah.
You need more?
Yeah.
More concrete.
Here's a little concrete. Not much.
With the area behind the shelf backfilled, the last side panel of level 15 was fit in place and found to have a rock preventing the panel from sitting level.
We're fitting panels, so it's going to slow down just a little bit.
Hold on the concrete.
That's what I was afraid of. Vertically down.
A diamond saw blade in a battery-operated grinder cut grooves, allowing a hammer and chisel to knock off pieces of the rock.
You want to put the level on it to see if it's straight up and down? Okay, Phil, here comes the panel down.
Yep, hammer it down. Whoa. Mine's got to come up now. I got to keep this turned. I can't lift. Lift. No. Here, I'll turn it. Yeah. All right, lift. 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 Got it.
Level 16 of the stainless steel replacement structure was finished on Saturday, July 10th, the last day of the expedition. The fabrication of the stainless steel frames continued with levels 18 through the top layer 22, built for the fall expedition, which commenced on October 1st, 2010. Throughout the 9-day expedition, members of the Fort Stanton Cave study project hauled bags of concrete, stainless steel frames, and high-density polyethylene panels through the mud and water of the main corridor, gradually working their way to Don Sawyer Memorial Hall and the stainless steel replacement structure. Once there, rocks were screened, concrete mixed, and panels lowered as the structure reached towards completion. To assist in reaching the upper levels, temporary scaffolding was built. A large rock in the lower right corner of the dig shaft prevented the upright from being installed, so levels 17 and 18 were partially installed, and then attention was focused on removing the rock using a drill, sledgehammer, and bullpins. Wood panels were removed to make room for the upper levels, and the remaining structure braced. Then another large rock in the wall was removed. A deck was put in place at level 19, and levels 20 through 22 were finally set in place. After level 22 was bolted together, backfilling was completed, and a concrete cap was poured around the perimeter of that final layer. With the completion of level 22 on Saturday, October 9th, the last day of the expedition, the main structure of the stainless steel replacement was finished, but there was still more work to be done. Over the ensuing winter months, when again Fort Stanton Cave was closed for bat hibernation, fabrication again continued with the stainless steel for the entryway passage and the new hoist for the shaft.
Okay, we done with this piece?
April 23rd, the first day of the 2011 spring expedition. Construction of the stainless steel hoist designed by Wayne Walker, began with a dry fit of the head frame upright. Some trimming of the wall was necessary, so Wayne Walker, Gary Grogg, and John McLean used a sledgehammer and a pry bar.
Yeah, I think we are.
Okay, then I'll pack up then.
Actually, they could use a piece of straw.
Yeah. In order to get this off, we may have to take all of that out.
Might have to, yeah.
What I'm looking at.
Plywood was used to keep debris from entering the shaft.
If you get that away, we could be done.
In order to maintain close tolerance, the mud was scraped off the mating surface of the head frame uprights and the bolt holes were wire brushed clean.
Based on the frame?
Well, the frame's right up here too.
Oh, but that's unnecessarily complicated. I'm just gonna measure.
What? That's fine, I'll come and get it in a minute.
Anti-seize compound was applied to the threads of the bolts.
Put 10 pounds in. I'm worthless. Concrete.
Over by.
We didn't. There's a bracket that goes front and back to this.
Yeah.
Right, an angle that goes down.
Yeah.
We may have to take some more out over here.
You just go down that hill, right? That big hill is just goes to the top of that.
This is going to have to come out.
You may have to take a little bit here, but this is going to have to come out right here.
So how long did it take us to get to this?
Of course, we're going to have to take some rock out of there anyway, so.
When did we go in?
Yeah, this makes it young.
It's 11:30.
After the hoist beam was installed between the head frame uprights, the angle brace and gate posts were prepared to be bolted to the uprights.
Those are.
The hoist beam and head frame uprights were constructed from the same 2 by 2 by 1/4 inch stainless steel angle iron that the stainless steel replacement structure's panel frames were fabricated from.
Jim and I teamed up and did a good job. I designed it, he built it.
The angle brace and gate posts, along with the gate, were constructed of stainless steel 1 by 1 tubing with a heavy-duty 1/8 inch wall.
You can safely say we don't need the.
After all the bolts were tightened up, concrete was poured along both sides of the top layer of the stainless steel replacement structure, thus completing the concrete cap. The whole time the hoist was being constructed, cavers with the Fort Stanton Cave Study Project were cleaning up in Don Sawyer Memorial Hall.
Drop it. All the way down, huh?
The old wood panels were disassembled, and the most rotten of the components were wrapped in plastic to prevent splinters from contaminating the cave. Over the winter months, the water in the main corridor receded, leaving a thick soup of mud, which all the old wood components had to be hauled through on the way to the surface. Upon reaching daylight, the trash from Don Sawyer Memorial Hall was deposited in heaps to await a trip to the dump. With the hoist completed, attention was focused on replacing the 30-foot-long wooden protection wall along one side of the Don Sawyer Memorial Hall entryway passage, which was installed in 2007 after the original low, tight belly crawl was enlarged to facilitate access.
I don't think it has screws in it.
3 days, April 24th, 26th, and 28th, were spent disassembling the wall and replacing it with stainless steel and high-density polyethylene.
Okay, we'll pass this down.
After the 2x4 support of each panel was excavated, the screws holding the plywood were removed.
Some screws in
Plywood
there, boards
and
ready
the
to
2x4 support
Now,
were
very
passed
careful.
down passage and taken to a site in Roaring Hill Passage to await transport
Take board
to the
down there.
surface.
Okay, here comes another one, a 6'8".
And that's the bottom.
No, that's the bottom right there, because the bottom, you said the bottom's about 11 inches or so.
Yeah.
So that's the top.
Yeah. Alright.
Oh, okay, so that goes together.
Yeah.
Because that other set's already there.
Right.
Okay.
Yeah.
Okay.
So that's the way it's going to go together with the plastic.
So we're going to bolt it through here,
Yeah.
and we're going to screw into the plastic there.
Right.
So we're ready for the plastic to come up next.
Right.
Wooden panels were removed one at a time and replaced to prevent a potential collapse of the
Does
passage.
it go long ways like this, Wayne?
No,
or-
it goes up.
So I need to rotate it and turn it up.
Yeah. Okay. Let me hand it down to you and we'll go behind this other one.
Oh,
No, no. Keep it upright.
keep it upright.
Yeah, we got enough space.
Okay, how's that look?
That's looking real good. You don't want to tighten these real tight because it's plastic you're going in.
Oh, let's strip it out.
Right.
Okay, got it. Barely
Voids
good enough.
behind the completed wall necessitated the backfilling of some panels. As the roof of the passage supported the stainless uprights, so the bottoms were concreted in place. When finished, the replacement entry passage wall consisted of 22 stainless steel upright supports and 9 high-density polyethylene panels. To recap, 3,145 holes were drilled, and considering the fact that each completed hole was pilot drilled first, which means each hole was drilled twice, a total of 6,354 holes were drilled in the stainless steel. 1,199 cuts were performed, and 5,012 inches of weld was laid down, which is equivalent to a bead 418 feet long. 860 nuts were welded to the structure. The total labor time for fabricating the stainless steel was 873 hours. If based on a 40-hour work week, that's 22 weeks, or 5.5 months. The calculated weight of the 101 stainless steel frames, 88 high-density polyethylene panels, 5 decks, uprights, braces, bolts, washers, and nuts is approximately 6,300 pounds, all carried a mile into the cave by members of the Fort Stanton Cave Study Project while volunteering with the Bureau of Land Management. Project members contributed 381 man-days, and if one assumes an average 10-hour workday, that works out to 3,800 hours, hauling and constructing the stainless steel and high-density polyethylene replacement dig support structure, which by design will allow continued access to Fort Stanton Cave's Snowy River Passage for many years to come.